Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, good morning and welcome to the SwayamPrabha course titled Marine Renewable Energy Systems. I think you will appreciate the contents of this course because this course is one of the pioneers in the sector of renewable energy, which is trying to teach and share research ideas in advanced level, which leads to analysis, design and development of new renewable energy systems. This will help the researchers, industrial partners, technology transfer officers, and of course the graduate students of various disciplines: civil, structural, offshore engineering, maritime engineering, marine engineering, aerospace applications, applied mechanics, energy systems, mechanical engineering, so on. So they will be able to apply these concepts as basic guidelines so that they will develop these ideas for innovative research. The principal aim of this course offered by Department of Maritime Engineering at IIT Gandhinagar under the SwayamPrabha portal is to develop Made in India concept and make India stronger and self-sufficient. as the vision of our Honorable Prime Minister. So IIT Gandhinagar is working in this front with starting the new Department of Maritime Engineering and exploring all high-tech possibilities of contributing to different sectors of maritime engineering to the growth of this country, as well as to keep and lead this specific area of engineering in the world domain. So friends, in the previous set of lectures, we discussed about the fundamental principles, analysis, design and development of wave energy converters as one of the modules of renewable energy sector. India being a peninsular country and Gujarat being the longest coastline in the country, wave energy harvest, which is not explored still to its highest optimum level in the country, should be attempted to have what we call blue economy. Made in India concept of harvesting wave energy and then supplying it to the grid systems along the coastal line of Gujarat as well as the nation will not only make the country self-resilient in power sector, but also bring down the cost of power distribution to the coastal sectors and coastal regions of livelihood to be a very minimum price. So, renewable energy systems, apart from supporting the economy of the country, will also help the social development of people living along the coast side. In addition, this can be also helpful for strategic application of naval defense all along the coast guards. So, friends, one of the other aim of objective of this course could be the design and development of wind farms. Onshore wind farms, which are land-based systems, are pioneer in the country in two states, particularly in Tamil Nadu and in Gujarat. So, I hail from both the institutions. I also am a full professor with IIT Madras, Department of Ocean Engineering, which is in Tamil Nadu, where wind energy is on the peak supply system generation in the country. Seconding to that is Gujarat, where I am also heading the Department of Maritime Engineering at IIT Gandhinagar, where Gujarat coastline is now actively involved in power generation using wind supply. In addition, thermal supplies are also very highly productive and leading in the country in Gujarat. So, in this lecture, friends, lecture number 23, we will talk about the analysis, design and development of wind energy harvest systems. This is a sequel lecture of 2 in number. So, this lecture number 23 is the first of its kind in this series of wind energy harvest system. So, welcome to this lecture, friends, on wind energy harvest system. The first question comes, what is the fundamental difference between wind and wave? Let us ask this question. Let us say the fundamental difference between wind and wave. So, the first thing, wave is relatively a high frequency phenomenon. Wind is a low frequency phenomenon. Wind energy is very high off coast, offshore. Wave energy harvest is also high, but sea state dependent. If we talk about the technological development of wind energy, or already proven concept. but wave energy devices are still in development stage. We can say wind energy and wave energy. Wave energy devices are water depth specific, needs an additional element or a component called the power takeoff mechanism to convert absorbed power to the grid. Whereas in wind farms or wind energy, this is not the case. You don't require any additional power takeoff mechanism. I will show you in detail in the lecture. Now let us ask a question as a structural engineer, as a maritime engineer. What should I bother when I design a wind energy system compared to wave energy system? So I will pay attention only to this first point as a maritime engineer. So when I say wind energy is a low frequency phenomenon, it is a large time period case, right? How does it bother my system? If I talk about, let's say, offshore wind energy harvest, I am looking for flexible systems. Flexible systems have two sets of periods. One is very flexible period, that is with a large time period. Other is very rigid periods, which is short time periods. Now let us try to apply the concept of understanding of this in a simple system of floating buoy. If the floating buoy has been understood with three axes as x, y, z, and the rotations about x, y, z, we have a specific name given to these degrees of freedom. Along x, the translation degree is referred to as surge. Along y axis, the translational displacement is referred as sway. You can easily remember this y and y matches. Along z or z axis, this is referred to as heave. So now surge, sway and heave are displacement degrees of freedom. Okay. In addition, rotation about x is referred to as roll. Rotation about y is referred to as pitch, and rotation about z is referred to as yaw. So now I could say roll, pitch and yaw are rotational degrees of freedom. By design, you could refer to other alternate courses in SwayamPrabha on maritime engineering. You will notice that the flexible systems have a combination of degrees of freedom which are flexible. For example, a flexible or a floating platform, let us say. To be very specific, I will refer this as floating offshore platform. The floating offshore platform, let us try to write down the degrees of freedom surge, sway, roll, pitch, heave and yaw. So, I have grouped them in a different manner, see that. So, displacement along x, along y and about z. These are all flexible degrees. Rotation about x, rotation about y and displacement about z. They are all rigid degrees of freedom. The typical periods, natural periods of a system in these degrees of freedom of any floating platform. We will take an example of a TLP, tension leg platform. Friends, what is a tension leg platform? How does it matter? We will talk about it slightly later, but there are other parallel courses offered by this department in SwayamPrabha where you can learn more about them. Simply Google and say TLP SwayamPrabha IIT Gandhinagar. You will get series of lectures on this delivered by me and my colleagues. So, you can also refer to those lectures for better understanding of what a TLP is. Now, coming to the argument of the tensional platform natural periods, about 100 seconds are the periods in surge, sway and yaw. About 5 seconds is the period in roll, pitch and heave. It means in these degrees of freedom, the platform is considered to be stiff. In these degrees of freedom, the platform is considered to be flexible. Okay? So, when you have got a platform which is floating in sea, which has got two distinct set of degrees of freedom together on the same design, we call such platforms as hybrid platforms. Generally, for offshore wind energy harvest, hybrid platforms are preferred. I will tell you why at the end of this lecture. So, hybrid platforms are preferred for offshore wind energy harvest. When I make this statement, when you accede to this statement, then you will notice that certain degrees of freedom have very large periods. So, we know the frequency and the period are inversely proportional. So, large period means lower frequency. Now, let us go back and understand the difficulty here. Wind energy or the wind is having low frequency phenomena. So, any low frequency phenomena will induce more forces and responses in degrees of freedom which are having low frequency. That is, the responses in surge, sway and yaw will be very large. Okay. Whereas, in other degrees of freedom, the response may not be that great. And you know, when the flexible degree, when the periods of these flexible degrees, when the natural periods of surge, sway and yaw matches with the natural period of wind, then the system will have a resonating response. So, therefore, the design becomes complex. Friends, please understand the classical difference between the design of an offshore wind farm compared to offshore wave energy systems. Offshore wave energy converters are designed to respond in the resonating band. If you carefully look at, we have designed a system example to resonate in a stiff degree which is heap. We showed you the whole design in the series of lectures in the earlier modules. So, on the other hand, in offshore wind energy systems, since the resonating response is invoked, the design becomes challenging. So, one has got to check that the design should not fail when the periods match with the degree of freedom and with that of the wind force exciting the system. I think now you are very clear about the greatest challenge in front of you when you start designing an offshore wind energy system, and the design concept itself is now deviated from what we had so far discussed with offshore wave energy converter systems. Okay? So, that is the fundamental difference which we have to understand in the beginning itself, so that we focus on this direction as we proceed in understanding this specific and the next following lecture. Hope you have any specific questions, please post to us to my email ID. We will be able to respond to you very quickly and support you for your questions. Friends, please note that renewable energy systems are being also sponsored financially by Government of India, Ministry of Renewable Energy, for project submissions and proposals, where you are able to create your own made in India concept designs and help Government of India to harvest wave and wind energies all along the coastal side, especially on the rural and very rural sectors. India has got the longest coastline and you are a peninsular country, and Gujarat has got the longest coastline within India. Therefore, we must attempt to design systems to take an advantage of the situation. Therefore, this lecture will be very helpful for you to provoke your research visibilities towards offshore wind energy systems. Having said this, let us see why the floating wind, offshore wind energy, which we call as floating offshore wind turbines, okay, are challenging. Floating offshore wind turbines, as shown in the figure, you can also see along X the response is surge, along Y the response is sway, along Z the response is heave, and about X roll, about Y pitch, and about Z yaw. So, if we start putting a wind turbine supported by some system in offshore, there are two ways I can locate these blades of the turbine. One, the axis of the turbine is horizontal. The other could be the axis of the turbine is vertical. Let us say the figure what you see on the screen has got horizontal axis wind turbine. So, there are two ways I can design this. One, with horizontal axis wind turbine, which you see on the screen. Can also design a system with vertical axis wind turbine. Okay. So, I have a vertical axis and the blades will rotate about this, right. I have an horizontal axis, the blade rotates about this. Okay. So, now interestingly friends, depending upon the wind direction, I will have a match of this rotation either with roll or with pitch. Okay, because the axis can be this way, can be this way also, right? Can be this horizontal also. So it can be either with roll, aligned with roll, or with pitch, correct? Whereas the vertical axis wind turbine align the response with yaw, is it not? This is yaw. So fundamentally, the design of these two turbines are different. In the first case, we are invoking responses along roll or pitch. In the second case, we are invoking responses along yaw. Of course, in both the cases, surge, sway and heave will be the determining parameters because the system is remaining floating. For a floating system, as we saw in wind energy, wave energy converters also, these three responses will anyway govern the stability of the floater. Okay? The stability of the floater will be governed anyway, controlled anyway by these three displacement degrees of freedom. No doubt about that. In addition to this complexity, it will also invoke responses either along roll or pitch or along yaw, being the case. So, in this specific lecture, we will not talk about the vertical axis wind turbine design at all. We will only focus on horizontal axis wind turbine, where the axis of rotation is about the horizontal axis and the blades are on the vertical plane. So, therefore friends, we are going to focus on the design and development of horizontal axis wind turbine located or fixed on a floater. Therefore, we call this as floating offshore wind turbine. So, here blades are placed on the vertical plane and they rotate about the horizontal axis, correct? So, that is why we call this as horizontal axis wind turbine. Okay? So, there can be usually 3 blades, but there are very special cases where there are 2 blades and there are 4 blades, I mean very specific cases. But usually very common is 3 blades. You would have noticed the system what you see on the screen here is similar to what you must have seen on wind turbines located along the land side. If you walk along Tuticorin in Tamil Nadu or maybe Jamnagar in Gujarat state, you will notice there are many numbers of wind turbines closely spaced all along the agricultural fields. As you drive along from Gandhinagar to Jamnagar, along the highway, you will find lot of onshore wind turbines located, and they contribute close to about 7% to 10% of the energy requirement of the Gujarat state. Whereas in Tamil Nadu, this focuses closely around 13 to 15%. It is very large compared to this, and we are now growing. We are investing more and more. So, what I am talking about here is not the wind turbine located on land. I am talking about floating offshore wind turbines, but the superstructure looks exactly similar. You know, to be very crude to understand this, we can say Wind turbine systems are similar to a table fan, which we call as a pedestal fan. You must have seen a pedestal fan. Crompton Greaves manufactures a pedestal fan, etc. A pedestal fan has a pole and has got a motor, and the blades are fixed to this, and is of course connected to power. Once you switch on the fan, it has got a big base. You must have noticed it's got a big base. When you switch on the fan, the blades rotate, isn't it? The blades rotate, and this rotation is activated by the rotor, which is a electrical powered motor. The motor actually rotates the blades, and that will give you air circumferenced on all the sides. When you control the speed of this motor, you will notice that the velocity of rotation, that is the angular velocity, which is the velocity of rotation, right, of the blades increase. As they increase, you will notice that there is a sound also coming, what we call as a noise on the rotor. Thirdly, you will see the rotor is also vibrating. Fourthly, you will see this vibration is transferred to the base also. This is the base. Furthermore, after long term of running of this motor, this gets heated. Is it not? All these features, friends, of a table fan are exactly applicable to this system. So, imagine that I am having a table fan fixed on a floater. So, the base of the table fan is the floater, but table fan works for the input power given, whereas offshore wind turbine generates power. Okay. So, there is a reverse mechanism happening in the rotor. Reverse mechanism happens in the rotor, where the rotor acquires power from the rotation of these blades, and that power is what we are harvesting. I think you can easily understand this technology, at least, because the designer has to understand the concepts first, otherwise the design cannot be successful. Okay. So, compare this with the table fan and compare this now with an offshore wind turbine. The base is a floating offshore platform. Okay. All these aspects what you see on a table fan will also happen on a floating offshore wind turbine. Okay. They are same. Having said this, let us ask a question: why do we need a floating offshore wind turbine? That is a good question. Offshore wind turbines are of main attraction due to many points. Friends, in offshore areas, wind energy is of a very high potential compared to land. You may ask me a question, why? Let us answer this. Let us compare this for our understanding. Let us say land and sea, or let us say land and open sea, the wind characteristics. In land, the wind speed is low, but in open sea, the wind speed is, I should say, very high. So, if you have a very high speed on wind on offshore, that is what we require for our, because this will make the blades to rotate faster. As the blade rotates faster, it generates more power. So, we need the wind source with very high velocity to blow. That can happen in open sea. That is the first difference we notice. Second difference, in land, to attain good speed, you need to have the wind turbines very tall. Approximately, the height of wind turbines located on land is about 20 to 25 meters from the ground, from the natural ground level. But you do not require this here. In offshore, you do not require that height of the tower. So, to be very specific, we call this tower as mast. To compare this with our table fan, this is actually the mast. Okay? This is also referred to as tower, but this is the mast. This base is the floating platform. We can briefly call this as a floater. Okay? So, therefore, since the height of the mast is reduced, then the structural design becomes simple. It is not easy, but I should say simpler compared to this land-based system. Thirdly, land-based wind turbines disturb the birds' migration. You will notice that wherever these land-based wind turbines are situated, the bird flying practically will not be there, because they will develop a sound which disturbs the flying characteristic of a bird. So, you are disturbing the bird migration, whereas in offshore wind turbines, this problem is or does not exist, because they are in open sea. Okay? And fourthly, offshore wind turbines can be moved, that is, they are highly portable, because you are locating them on a floater. The floater can be moved at any location you want, whereas land-based wind turbines are non-portable. Once you fix it, they are fixed, that is all. You cannot move them. They are portable when they are located on floaters. So, we are talking about floating offshore wind turbines. So, there are many comparisons what will make you advantageous as far as offshore wind turbines are concerned compared to land-based systems. Let us look at the literature and look at the model where such wind turbines exist. You can locate a wind turbine above a semi-submersible. Semi-submersible is a floating offshore platform which is used for oil and gas exploration. If you do not have this system to harvest offshore oil and gas exploration, you can use this as an ancillary system to support wind turbines. China has started doing this. Indonesia has started investing on this idea. Korea, South Korea is now gradually thinking about investing on this sector. Then why not India? The second could be a spar platform. So, friends, semi-submersible, spar, tension-leg platform and barge are not covered in detail in this series of lectures. But however, we have one more SwayamPrabha course Introduction to Maritime Structures, which is also hosted by IIT Gandhinagar. Please go through that course in parallel to understand more about the dynamic, mechanical and structural behavior of these kinds of offshore platforms. Having said that, if you look at the plan view of these kind of wind turbines, they are different in shape in plan. Okay, the top view, they look like this, because spar is a cylindrical platform. TLP is again a cylindrical or a square hull which can host blades on multiple directions. Please note friends, we can have different structural forms of the superstructure compared to the substructure supporting them. So, in this series of lecture, we will discuss two things, where we are going to discuss about the design and development of an offshore wind turbine on a spar platform, compare that quickly with the tensionless platform, and also I take this advantages to a new system of Triceratop, which is a complete novel study what we carried out in our research group. So, friends, as I said, there is an utter necessity for investing on floating offshore wind turbines because of various reasons we explained in the previous slides. Taking it forward, let us understand the difference between spar supported wind turbines and other systems in parallel. Spar, which is expanded as single point anchor reservoir, is a deep draft compliant structure. Compliancy refers to flexibility. So, spar is a complete flexible platform having a geometry of a cylinder. So, the support system is just a cylinder. The cylinder is connected to the seabed using cables, which we call as mooring lines. So, it has got a hull, it has got a deep draft sill, and then it has got a mooring line. On the hull, I fix the platform. So, it is as good as a table fan fixed above the hull of a spar platform. Now, the hull of the platform is governed by ballast weight at the bottom. Ballast is an additional weight imposed on the platform to maintain its stability. As I said, this platform is completely floating because it is not anchored to the seabed is here, it is not anchored to the seabed, it is only connected through mooring lines to the seabed, it is not resting on the seabed. The platform is not like this, okay? The platform is like this. When it is floating, because of its buoyancy, we know when buoyancy exceeds the weight of the platform will float. I mean, any body will float, Archimedes principle, right? When the platform is floating, to maintain its flotation stability or hydrostatic stability, we need to ballast the platform by external weight. Usually, this ballast is provided at the bottom. By providing ballast at the bottom, the center of gravity of the platform shifts downward. Since it is a deep draft system, the center of buoyancy shifts upward, okay? Because this is flotation, this is weight. Now, the mooring system can be of a different profile it can be anchor spread mooring system, it can be catenary mooring system. Essentially, the mooring system is used to place the platform in position. For example, if you do not have these mooring lines, the platform will still float, but it won't remain at one location, is it not? It will keep on moving. To avoid this, to restrict this, to restrain this motion, we connect this platform with mooring lines. So, mooring lines help position restrain of the platform. Okay. Friends, as I said, to know more about the dynamic response behavior of offshore systems like SPAR, please refer to another SwayamPrabha course offered by Department of Maritime Engineering. The title of the course is Maritime Structures, offered by Department of Maritime Engineering at IIT Gandhinagar. Please refer to this course contents to know more about the dynamic behavior of a spar platform. So, the mooring system helps to restrain the platform. The platform now floats with high degree of stability. I provide the superstructure onto this. Remember friends, the connectivity design between the mast and the hull is not discussed yet. You cannot simply bolt it. It needs a firm connection. We will talk about this later. So, now the blades rotate or fix on the vertical plane. They rotate about horizontal axis. So, I could say now this is an horizontal axis wind turbine where the blades are fixed on the vertical plane. Okay. This is about the spar platform mounting the wind turbine. Let us look at the TLP, the tensioner platform supporting a wind turbine. Tensioner platform is a vertically moved complaint offshore platform. Let us say the TLP, which is abbreviation for a tension-like platform, looks like this. It has got columns, and it has got pontoons, okay. Now, these are called as column elements. These are called as pontoon elements, and I refer this hatched portion as hull. Okay. If I mark the water level, now this is a box. So, I could say this is a box which is hollow inside. Since the weight of the box is much lesser compared to its buoyancy, how can you say that? Because buoyancy depends on the displaced volume, is it not? So, the displaced volume is very large because the approximate size of a TLP is about 90 meters by 90 meters by 30 meters. It is a very huge box, but the column size is only about 12 to 15 meters in diameter, and they are also hollow tubes. So, you will notice that the weight of the platform will be very less compared to the displaced volume. So, since the buoyancy force is proportional to the displaced volume, I could say buoyancy will exceed the weight by a large number. So what does it happen to the system? This will make the system to float. Now, the difference between buoyancy and weight need to be compromised for static equilibrium. So I should say now W plus something should be equal to buoyancy. Now please see the direction of application of forces. W acts downward, buoyancy acts upward. So I should have a force now which will have to act downward to equalize this static. This is called equation of static equilibrium. So what is this component which will help the system to remain in static equilibrium? So I should now connect this to cables on all the four corners, anchor them to the seabed and provide initial tension to these cables. So now I have, if I call the initial tension in the cable as T naught, since there are 4 cables, I should say this is 4 T naught. So now, when the initial cables are provided in tension, they are called pre-tensioned. I won't call them as cables, I call them as tethers. Okay? Now it's very simple, friends. If I remove these tethers, what will happen to the system? The system is positive buoyant because buoyancy exceeds the weight, system will float. Is it not? It won't fail, remember, it will float. It won't sink, it will float. So system will float. So what I now do? I provide a table fan above this. I call this as floating offshore wind turbine. Okay. So now this is the wind force acting on the system which will make the blade to rotate. When the blades rotate, the rotor will capture the rotation, convert them to mechanical to electrical power, and the power is supplied to the generator. So that's how I harvest wind energy through this system. So let us go back to understand how a TLP supports a wind turbine. TLP is a vertically moved compliance system. The taut mooring lines, also called as tethers, will support the system because the system is designed to have with excessive buoyancy. Just now we discussed that. The columns of this TLP are tubular sections due to which the buoyancy force will exceed the weight of the platform, and this equation is what we have discussed in the previous slide as well. W is the weight of the platform, T0 is the total initial tension, and buoyancy is acting upward. So now we have a system like this which supports the offshore wind turbine. The third one which we are interested in discussing and making a presentation to you is a new kind of a platform which is called Triceratop. It has got 3 buoyant legs connecting the hull, and 3 buoyant legs are again axially connected through tethers to the seabed. So it is a floating system similar to a TLP and spar. Then what is the difference? The difference is the hull and the buoyant leg are connected not rigidly but by a ball joint. So the ball joints connect the buoyant legs to the deck. This is a conceptual platform which is novelly prepared, patented, technology transferred, now in commission by my research group at IIT Madras and now at IIT Gandhinagar. So, the system is similar to what we see in a typical offshore oil and gas production platforms facilities, but now this can be also used to support a wind turbine. So, now we have got three systems. One is spar supporting a wind turbine, other is TLP supporting a wind turbine, the third one is triceratop supporting wind turbine. So, we will compare a numerical model of all these three results and see among these three which is superior to hold a wind turbine offshore. So, now to do this, we have taken a primary design based on the high wind Scotland wind farm, which is also a floating offshore wind turbine, which is resting on a spar. The high wind Tempen wind farm located in Scotland was originally designed to rest on a spar platform. The depth of operation is 1000 meters, friends. It is not the distance from the coast, I am talking about the depth of operation. The water depth at which this wind farm is located is 1000 meters. So, we took this as a primary design available to us, compared that with the same system resting on a triceratop with aero hydrodynamic coupled model. The aerodynamic loads are extracted from open source domain OpenFast, which are then coupled in ANSYS workbench to carry out the coupled aero hydrodynamic time domain analysis. So, at this point of time, I must thank credits to Dr. Yogesh, who helped me in carrying out this study by comparing the high wind Scotland wind farm located on a spar with its behavior which is fixed on a triceratop, which I will be discussing. Let us quickly see the characteristics of this particular system. High wind Scotland wind farm, which is resting on spar, has got a diameter of 15 meter, the length is 100 meters, that is height of the tower is 100 meters. I am talking about the spar platform, and draft is 85 meter. So, out of 100 meter, 85 meter is in water, 85% is in water. That is what we call as deep draft systems. It is installed at 1000 meter water depth. We now compare this with the new model of triceratop, which also has the similar systems, but the buoyant legs are 3 in number. The area of the deck is about 2700 square meters, the large system. Okay. The mass, the variable ballast for both the systems are indicated on the screen. Furthermore, the hull mass, the tower in terms of its weight, which are kept same in both the cases. Then the center of gravity and the moments of inertia for the design of the mast, which are kept same in both the designs, are expressed in this table. So, nothing has been altered, including the hull mass, except the hull mass is changed here because the size of the triceratop hull is different from that of a spar. Okay. Rest of the tower, the turbine details, which is 5 megawatt turbine, and the cables and moorings are kept more or less similar. Wherever we want to change them as per the design, it will be indicated here. So, we have used the polyester cable and the power cable, both chain and polyester cable, for mooring the platform. Let us look at the NREL 5 megawatt wind turbine characteristic. The rating of the turbine is 5 megawatt, 3 blade configuration. Rotor diameter is 126 meters, hub diameter is 3 meters and hub height is 90 meter above the hull. So, we have used the Kymot spectrum model for turbulence spectral density. Category B, mean wind speed at the hub height is taken as 12 meter per second, it is fairly high, 12 meter per second. You can convert this to kilometer per hour. You will notice that the speed of the wind is fairly high here. The reference height taken for the study is 90 meters and the wind speed variation, the reference wind speed is 12 meter per second, the reference thickness is 90 meters and alpha in the wind model is taken as 0.2 and this is the wind profile being used to subject to this turbine, which is a 5 megawatt wind turbine NREL. The methodology followed in the analysis is the geometry is created using ANSYS space climb, then hydrodynamic diffraction analysis carried out, irregular waves is subjected to the triceratop, aerodynamic analysis used using open fast code, then time domain analysis is deployed to carry out aerodynamic response analysis. The stability is carried out for the platform. Once stability is ensured, time domain analysis is carried out, results will be discussed. So, friends, we come to the summary of this lecture. In this lecture, we discussed about the necessity of offshore wind turbine, what are the difference between wave and wind characteristics, why we should be careful in floating offshore wind turbine design. We have understood the comparison of spar, TLP, semi-submersible and triceratops supported wind turbines. We have taken a specific example problem of a wind turbine resting on a spar, then we modulated this to the same wind turbine resting on triceratop and we will show you the results in the next lecture. Thank you very much. Stay connected. Namaste.